So once astronomers confronted the direct evidence that the surface of Venus must have completely repaved itself not too many 100 million years ago, they realized that that made sense for a planet nearly as big as Earth with a crust that wasn't so efficient at releasing heat. The crust of Venus traps the immense internal heat of the planet and holds it in until that heat completely melts the crust all the way through, until we have nothing but molten lava at the surface. And then the internal heat escapes very well through that, and the crust re-solidifies and then holds and traps the heat for the whole planet again for another several 100 million years before there's so much built up heat that once again the crust completely melts. And then all the heat is released, the crust reforms, and the whole cycle repeats probably about every half billion to billion years or so. So it wouldn't have done this too many times in the history of Venus. I've been able to, in my kitchen, create something rather similar with a pot of boiling tortellini. You can have a layer of tortellini locked at the top of your pot where all the tortellini are held in place, kind of like a crust. And the heat energy from below in the pot builds up. You can see that the heat is trying to escape through holes in the tortellini. That would be analogous to the volcanoes. But eventually there's just so much heat driving so much pressure from below that all the tortellini turn over. And all the heat comes out through all of that. It becomes chaos for just a few seconds, and then a whole new layer of stable tortellini form on top, hold the heat like a cap. The heat builds up, and then bloosh, a rearrangement again, and you have a new layer of stable tortellini. The crust of Venus seems to be working something like the tortellini. So we can be very glad that we do not live on a planet where that happens. But remember that Venus is a planet that in all of its bulk properties is very, very, very similar to Earth. So how did it come out so profoundly, hellishly different? Well, it all may have come down to just one single, solitary key thing. No liquid water oceans. On Earth, liquid water oceans absorb carbon dioxide and process it through the rocks into a CO2 cycle. On Venus, no liquid water oceans at all mean that carbon dioxide from volcanoes just piles up into the atmosphere and piles up over the entire 4.5 billion year history of Venus. CO2 continues to build, and now we have an atmosphere of 95% CO2, and the sheer quantity of it is so much that it's 90 times denser than earthly air. And that led to the most powerful greenhouse effect in the solar system, and a surface temperature hotter than even the sun-facing side of Mercury, which dried up the crust and also softened it, made it more squishy. It turns out that when you chemically add water molecules into rock, you make rock more brittle. So drying up the crust made it more flexible. So that made plate tectonics impossible. Plate tectonics requires a thin, brittle crust. And we ended up on Venus getting a thicker, somewhat more bendable crust. And no plate tectonics, so no very efficient mechanism like Earth has for releasing all of the internal heat. On Earth, so much comes out at the plate boundaries. And, well, for reasons just described, that results in a surface going molten every half billion to billion years. Whew. Change one little thing, and you could completely ruin the Earth in the same way. Since Venus is just a little too close to the Sun to retain liquid water oceans, astronomers have invented a concept called the habitable zone, inner boundary. Our solar system's so-called habitable zone is the range of distances out from the Sun where a large enough terrestrial planet with a good atmosphere could retain liquid water on the surface, like Earth. Venus is apparently just a little too close to the Sun to lie inside that zone. Although perhaps there is just a little more to the differences between Venus and Earth. As we've been mentioning and discussing how there's no erosion on Venus, Venus rotates very, very slowly. Slowest rotating planet in the solar system. 1 turn in 243 Earth days. That's even longer than it takes Venus to orbit around the Sun. And it rotates backwards from all the other planets. You could say it rotates super slowly upside down, but it's easier to just simply say it rotates super slowly backwards. And the best guess for how it could have been set up that way would be an enormous impact that would have knocked most of Venus's initial rotation speed out and left it almost not turning at all, but turning slightly backwards. Not all astronomers are completely convinced that that's how Venus got its funny rotation, but it seems to be the most natural explanation. And apparently, as a consequence of its very slow rotation, Venus has no significant magnetic field. Presumably, Venus has liquid metal in its inner core, since it is a planet of similar size and composition to Earth. But it's the rotation of the Earth that stirs up the movements in that liquid core that generates the magnetic field. Without a rapid enough rotation, a planet like Earth lacks a magnetic field, and that means the solar wind is impacting directly onto the upper atmosphere of Venus. However, unlike Mars, Venus's atmosphere is just so extremely dense that the proportion of total atmosphere loss is very, very small. You can blast away a fair amount of the Venusian atmosphere and barely put a dent in how much air would remain. Although perhaps it isn't just that Venus was too close to the Sun for liquid water oceans to form that caused Venus to come out so differently. It could be that the lithosphere of Venus already was just a little bit too thick for plate tectonics to occur. Since Venus is a slightly smaller planet than Earth, we would expect it to have had a slightly thicker lithosphere. And we do not know exactly how thin the lithosphere needs to be for plate tectonic action to start up. So if Venus had a thicker lithosphere from the beginning, it might never have had plate tectonics and been in that regular melt-down, squishy crust, melt-down, squishy crust cycle ever since its inception at the beginning of the solar system. Yet, most experts do agree that plate tectonics ought to have been possible on a planet the size of Venus that would just be cooler, just not have such a crazy greenhouse effect. That should have made the crust brittle enough. But more research and exploration of Venus is definitely needed. Indeed, of all the terrestrial planets in the solar system, Venus is the one that we understand the least. And it has been very poorly explored because of the difficulties of studying the surface of Venus. We really do not know enough about it. What we would want to land on this planet is some kind of seismographic station so that we could record Venus quakes and get a good look at exactly whether the lithosphere is thinner, thicker, whether we have an inner core and an outer core and a mantle like Earth or something different. We simply don't know. And establishing some kind of lander on Venus that can function for more than a few hours is proving very, very, very challenging indeed. And while your textbook mentions some recent spacecraft that were launched to Venus and are successfully arriving, their purposes are entirely to study the atmosphere of Venus and not the surface rock or the interior. Indeed, in planetary science, we are especially concerned that the expertise in Venus's interior is retiring and dying of old age, and not being replaced by new young researchers who will have new lander probes to give them new data.